Hi everyone. Today we're going to do section 7.1 and 7.3. Okay? 7.1 and 7.3. 7.1, now we're discussing radical expressions. Okay? Radical expressions. First, we will start with the following statements. Here's my first statement, okay? Which is this, look. This is section 7.1 and 7.3. Okay? I'll come back later with 7.2. All right. In 7.1, let's first say the following statement. A is the square root of B if A squared equals B. Okay? Well, we'll give some examples of those. First example. 2 is the square root of 4. And why is that? Since 2 squared equals 4. 2 is the square root of 4 because when you square this, you get 4. Here's another one. 3 is the square root of 9. And why is that? Since 3 squared is 9. Okay, here's another one. 4 is the square root of 16. Why? Because since 4 squared equals to 16. That's why. And you can go on ahead and do 5. 5 is the square root of 25, since 5 squared equals 25. 6 is the square root of 36, since 6 squared equals to 36. And so on and so forth, okay? But here's another one. Here is one more. Okay? Note, please understand that the only reason why this is true, 2 is the square root of 4, is because when you square this, you get 4. When you square 3, you get 9. So therefore, 3 is the square root of 9. When you square 4, you get 16. So therefore, 4 squared, because 4 squared equals 16. Okay? So 4 is the square root of 16 because 4 squared equals 16. Maybe that's the better way to say it. Okay. In addition, we can also say the following. By the way, is there another number such that when squared you also get 4? That's a question. Is there another number such that when squared you get 4? The answer is yes. It's -2. -2, when you square it, you also get 4. So we can say the following. -2 is the negative square root of 4. Yes. Why? Since negative 2 quantity squared equals 4. So therefore, it seems to me that 4 has 2 square roots. The positive case and the negative case. 4 has 2 square roots. Here's another one. Negative 3 is the negative, okay? Negative. Gotta say that. Negative. Square root of 9, since negative 3 squared equals 9. Okay, you guys do this one. 16 has 2 square roots. I gave you the first one. 4 is the square root of 16. There's another one. Negative 4 is the negative, okay? Gotta say negative square root of 16, since negative 4 quantity square equals to 16. Yep. Okay. So therefore, 4 has 2 square roots. The positive case and the negative case. 9 has 2 square roots. The positive case and the negative case. Okay. I don't know about you guys, but every time we discuss this, I do not want to write the entire sentence. Okay? No, it's too much work. Instead, why don't we write mathematical notation? Okay? Here's the first one. For this first one, look, we can say 2 is the square root of 4. Why? Because when you square this 2, you get 4. How about this one? Negative 2 is the negative square root of 4. Yes, that's what this one is saying. Right here in red. Maybe I should write it in red. Let me write it in red. Let me get my eraser. I'll write this one in red. How's that? Okay. Negative 2 is, look, the negative square root of 4. Why? Because when you square negative 2, you get 4. And 4 is called a radicand. Okay, the radicand. This 4 is called a radicand. This negative 2 is the root, the square root. So therefore, this is that when you square this root, you better get the radicand. When you square negative 2, you better get 4. Okay, let's do this one. This is better notation because we don't have to write a whole sentence. 2 is, I'm sorry, not 2. I already did 2. How about 3? 3 is the square root of 9. Yep. Why is that? Well, because when you square this root 3, you better get 9. And you do. Okay. How about this one? Negative 3 is the square root of I'm sorry, I better say negative, right? I better say negative equals to negative square root of 9. Yep. Why? Because when you square negative 3, you get this. How about that one? I'm going to switch the sentence over. I'm going to say the square root of 16 is 4. Is that a true statement? Yes, it is. Because when you square 4, you get 16. Yep. When you square this root, you better get the radicand. This is called a radicand. Okay. How How about that one? The negative square root of 16 equals to negative 4. Is that a true statement? Yes, it is. How can we verify that? We can verify it by squaring this negative 4. When I square this negative 4 and I get this positive 16, this is a true statement. Okay? Is negative 4 squared 16 the radicand? The answer is yes. So that's a true statement. Okay, very good. Okay, so I'm running out of room, so therefore, have to erase this, guys. But I'm gonna give you more examples, okay? Gotta erase this, sorry. So this is gone. Okay, so now, here's another one. The square root of 25. What we're looking for is a value such that when squared, you get 25. What value squared equals to 25? The answer is 5. No problem. Okay? When you square this 5, you get 25. By the way, this is called the root. 25 is called the radicand. Radicand. Okay. Here's one more. The square root of negative 49. Okay. We're looking for a value such that when squared, you get negative 49. Okay. If you say 7, is 7 squared equals to 49? If your answer is 7, put a question mark here. If your answer is 7, now if you square 7, do you get 49? Negative 49. Let's see, 7 squared equals to 49. Oh, no. So therefore, this is not true. That's not a true statement because when you square the 7, you don't get negative 49, you get positive 49. Okay? If you answer negative 7, well then you ask yourself, does negative 7 quantity square, does that equal to negative 49? What's negative 7 squared? 49. We didn't get negative 49. So therefore the answer is not 7, and the answer is not negative 7. Okay, wait a minute. So we're going to say the square root of negative 49 does not exist. So therefore, we're going to say the square root of negative 49 does not exist. Why? Because if you say 7, when you square 7, you get 49, not negative 49. If you say negative 7 squared equals 49, not negative 49. So therefore, the answer does not exist. Okay. Well, let's ask the following. What is the negative square root of 49? Okay, wait a minute. If you say negative 7, the answer is correct. Why? Because when you square negative 7, you get 49. So this is true. Negative 7 quantity square equals to 49. So that's a true statement. Okay? The answer is -7. So, okay, so what did we learn from here? We just learned that when the radicand is negative, when the radicand is what's inside, under the radical. This is called the radical. The square root is the radical. When the radicand is negative, and we're talking about the square root of a negative number does not exist. When the radicand is negative, the square root of a negative does not exist. In other words, if you have a negative under the square root, it does not exist. But if you have a negative outside the square root, that does exist. The answer is negative. Okay. All right. If the negative is under the square root, does not exist. If the negative is outside the square root, it does exist. Yes, it does. Okay. So therefore, the square root of -100, what? Tell me. Does not exist. Because the negative is inside. What about the negative square root of 100? What is it? -10. Okay, that one does exist. That was the square root. How about this one? What about the cube root of 27? Okay, so now we're looking for a value such that when cubed, you get 27. The answer must be 3. 3 times 3 times 3 gives you 27. Okay. What about the cube root of -27? Okay. Now you're looking for a value such that when cubed, you get -27. Okay. Well, -3 cubed is what? -3 times -3 times -3. What is that? -27. Wait a minute. If the negative is under the cube root, that does exist. Yes, it does. If a negative is under the square root, that does not exist. This one does. This one is -3. Why? Because when you cube this, you get -27. Okay? In fact, whenever they call this the index, this is the index. Okay? That's the index, guys. And the -27 is the radicand. The radicand. Okay? When the radicand is negative and the index is odd, that does exist. Yes, it does. Yes, it does. When the radicand is negative and the index is odd, That does exist. Yes, it does. It does exist. But if the index is even, this is 2. This is 2, the square root as 2. If the index is even and the radicand is negative, that's not possible. No, does not exist. Okay? We have to remember that. So therefore, look at this. The cube root of negative 64. Is there an answer to that? Yes. Yes, there is. The answer is what? Negative 4. Why? Because when you cube, you see this index 3? So you got to cube this. When you cube negative 4, do you get negative 64? The answer is yes. So that one does exist. How about this one? What about the square root? The square root of negative 64. What about that one? Does not exist. Does not exist. Why? Because the index is 2 even. When the index is even, this radicand cannot be negative. If the index is even and the radicand is negative, it does not exist. But if the index is odd and the radicand is negative, that does exist. Yes, it does. Okay. All right, very good. Excelente. All right. Okay, let's not forget that, okay? Once again, I'm going to say for the last time. If the index is odd, the radicand can be positive or negative. Okay? If the index is even, the radicand cannot be negative. No, it's got to be positive. Okay? If it's negative, it does not exist. All right. More examples. We're doing more examples. Here's another one. Here's one more. Watch this. Okay, so I'll ask you some good ones. What is the square root? We already know this one, okay? What is the square root of 49? Well, the answer is easy, 7. Okay, no problem. What is the square root of 64? Oh yeah, the answer is easy, no problem, 8. Okay. What is the square root of 81? Oh yeah. We have confidence. You know the answer is 9. No problem. Easy. Morales, that's too easy. Okay. What is the square root of 100? Oh, too easy. Confidence. We're confident. Too easy. 10. Okay. Fine. So, okay, that's too easy. Or let me ask you the following. What is the square root of 50? Uh-oh. Wait a minute. Say what? Yeah, what's the square root of 50? Okay, so we're stumbling now. All I did was add one more to that. We're stumbling. It's not easy to answer this one. But okay. The square root of 64, 8, right away. What about the square root of 60? Uh-oh. We're stumbling now. Okay? We don't know. Square root of 81. We got confidence. Oh, yes, 9. Okay. What is the square root of 80? Uh-oh. The square root of 100. Oh, yeah, no problem. 10. Okay. What is the square root of 98? Uh-oh. Uh-oh. So what's the problem? Why is it that the square root of 49 we answer right away, but the square root of 50 we stumble? The square root of 64 we answer right away, but the square root of 60 we stumble. No more confidence. The square root of 81 is 9, but the square root of 80 we stumble. Okay? And the square root of 100 with confidence, 10, but the square root of 98 we stumble. You know what the problem is? The problem is the following. Whenever the radicand is a perfect square, we can answer that with confidence. But if the radicand is not a perfect square, we stumble. Look at this radicand 64. The square 64, 8, because that's a perfect square. But the square 60, we stumble because 60 is not a perfect square. The square root of 81 is 9, because 81 is a perfect square, but the square root of 80, we stumble because 80 is not a perfect square. The square root of 100 is a perfect square, so with confidence we answer that question, but the square root of 98, we stumble because 98 is not a perfect square. That's the problem. Okay. So it seems to me that whenever the radicand is a perfect square and we're taking the square root, we can do that one right away. So I'm going to write the following statement. We love radicands that are perfect squares. I like an S. Okay. Nope. I'm discussing the square roots, okay? This is for square roots. Whenever the radical, the index is 2, okay, whenever the radical is the square root, okay, we want to see perfect squares. We love radicands that are perfect squares when the index is 2. Okay, look at this. If there's a perfect square, we answer the question right away. What's the square root of 49? 7. What's the square root of 50? We stumble. What's square root of 64? 8. What's the square root of 60? We stumble, right? What is the square root of 81? 9 with confidence. What is the square root of 80? We stumble. So it seems to me, if you look at all of this, whenever the radicand is a perfect square, we have confidence. We love them. But if the radicand is not a perfect square, our confidence is gone. So we love radicands that are perfect squares. We love this one, we love this one, we love that one, and we love that one. That's what that is saying. Let me show you what to do about this one. Okay? So here. If the radicand is not a perfect square, comma, then we will factor the radicand looking for what we love. Okay, don't forget, we're talking about the square roots, okay? Index 2. But if we change the index, you can still apply this, okay? If the radicand is not a perfect square, I'm showing you what to do when the radicand is not a perfect square, when the index is 2. If the radicand is not a perfect square, comma, then we will factor the radicand, I don't know if we need this, looking for what we love. Okay, you see this one? This one here, 50, not a perfect square, no problem. Let's follow this. If the radicand is not a perfect square, this one, not a perfect square, we will factor the radicand. Factor means express it as a product. In the product, you want to find what you love. What you love under the square root are perfect squares. So I'm going to factor 50. And I want to find a factor of 50 that's a perfect square. Okay? All right, give me a second, guys, okay? All right, so we're back. So 50, not a perfect square, no problem. If the radicand is not a perfect square, then factor. You want to highlight factor. Highlight. You want to highlight factor right here. Highlight factor. Okay, underline it. So if people see it, you wanna factor, highlight factor. Okay. So we're gonna factor this. And we are looking for factors that are perfect squares because that's what we love. Okay. 50 is 25 times 2. Hey. 50 equals the square root of 50 equals to the square root of 25 times 2. That's 50. But when you see 25, we love it. We love this 25. Put a heart there. We love that 25. Why? Because 25 is a perfect square. Okay. What is the square root of 25? 5. So therefore, that's going to come out. Note, the square root of 25 is 5. So we can find the square root of 25. There's nothing you can do about this. This 2. So therefore, a 5 comes out. The square root of 2. And that's all you can do. There we go. Okay. So now I know how to simplify this. This is what you're going to use to simplify the square root of a number that's not a perfect square. You're going to factor that number looking for what you love. If you cannot find factors that are perfect square, that's not your fault. It's no one's fault. It's just the way it is. How about this one? Let's find factors of 60 that are perfect squares. Okay, you don't have to do it all in one step, guys. You can just break down to 60. Watch this. You can do this. 60. 60 is 2 times 30. 30 is 2 times 15. 15 is 3 times 5. So what are the factors of 60? 60 is 2 times 2 times 3 times 5. But you see this pair of 2's? This pair of 2's is going to make a perfect square. What's 2 times 2? 4. This is a 4. You see this 3 times 5? There's nothing you can do about it. It's not your fault. So this one is 15. Okay? So therefore, you can say, you don't have to write 15, but you can say 60, the square root of 60 is going to be the square root of, I know it's a 4 there, and now you can write 3 times 5, but I'm going to write 15 times 15. You love this 4. This is love right there. This one, I don't know. Nothing we do about it though. So therefore, the square root of 4 is 2. How about the 15? It's not your fault. Just leave it inside the radicand. Okay, the radical. 15. There you go. You have simplified this. You guys go ahead and simplify this one. I'll give you guys a few seconds. Okay? All you have to do to simplify this one is factor the 80, looking for what you love. What you love under the square root are perfect squares. Okay? So therefore, 80. Let's factor 80. And there's many ways you could do this, okay? I just show you one way. Here's another way. 80 is 2 times 40. You don't have to break it down all in one step. 40 is 2 times 20. 20 is, you could say 4 times 5. 4 is a perfect square, okay? And this is also 4. When you take this 4 and you multiply times this 4, that's 16. So no, 80 is like this. It's 2 times 2, and this 4, another 2 times 2, and this 5 times 5. You see this? That's a perfect square because that's 4 times 4. That's 16 times 5. That's 80. But you love the 16. The 5 you don't care for, but it's not your fault. It's just part of the problem. Don't blame yourself for it, okay? So therefore, the square root of 80 is gonna be the square root of 16 times, I should write it in black, okay? Because then you can highlight what you love. So this 80 is the square root of 80 is 16 times 5, but the 16 you love. Put a heart there. You love the 16. The 5 you don't care for. Okay. And so therefore, what is the square root of 16? 4, the square root of 5. How about the 98? Can you do the 98, the square root of 98 right away? Well, you better factor 98. Okay, let's factor 98. Okay, what is 98? 98. Well, 98. Let's start with 2. 2 times what gives you 98? 2 times 49. Hey, right away. 49 is a perfect square. So therefore, good class, watch this. The square root of 98 equals to the square root of 2 times 49. You love the 49. Put a heart there. Because 49 is a perfect square. So what's the answer? I'm showing you how to simplify this one, this one, this one, that one. This is the way you simplify it. The answer is like this. Answer. A 7 comes out. The square root of 2. And there you go. Okay. We know how to simplify radicals. This can be applied even if the index is no longer 2. Let me give you an example. Here's another one. Here's this example. Watch this example. What is the cube root of, let me see. Here's a good one. What's the cube root of 81? Okay? Cube root of 81. All right. So here's a good question. Do you love this 81? That's a good question. Do you love the 81? The answer is right now, no. No. I don't love this 81. Right now I don't. I used to love this 81 when the index was 2. The square root of 81, I love the 81. Yes, I do. This should be within the heart because it's a perfect square. The answer is 9. But not here. I don't love the 81 anymore. I used to love the 81 when the index was 2. But if the index is 3, I do not love the 81. Because now I am no longer looking for perfect squares. I am looking for perfect cubes, but I'm still going to follow this rule. If the radicand is not a perfect cube now, if the radicand is not a perfect cube, then we will factor the radicand looking for what we love. When the index is 3, we love perfect cubes. We no longer love perfect squares. We're not talking about this. So let's just follow the rule again. Now we're looking for perfect squares. Perfect cubes. We want perfect cubes, look. So let's take the 81 and let's factor the 81. Lucky for us, 81. We can do this 9 times 9. And 9 is 3 times 3. And this 9 is 3 times 3. So 81 is 3 times 3 times 3 times 3. But now I'm looking for perfect cubes, so I'm going to take 3 of them. When I was looking for perfect squares, I would take 2 of them. 3 times 3. But now we're looking for perfect cubes, so 3 times 3 times 3, that's 27 times 3. This is what I'm looking for now, because the index is 3. So therefore, I do not love the 81, not when the index is 3. So this is the cube root of what? 27 times 3. 27 times 3. And 27 we love. Yep, because it's a perfect cube. What is the cube root of 27? A 3. So therefore this equals to 3. A 3 comes out, and this 3 is left behind in the house or under the square root, under the cube root. The cube root of 3. And that's all you could do for that problem. Okay. Here's another one. What is the cube root of, let me see. What is the cube root of 64? Do we love the 64? Well, not here. No, not here. Why not? Well, because now we want perfect cubes. If the index was a 2, yes, we love it. But because the index is a 3, we don't love it anymore. I don't love the 64 because it's not a perfect cube. Let's follow this. If the radicand is not a perfect cube, then we will factor. Okay, let's factor 64. Looking for what we love. So 64. Try, I don't know, you could try 8 times 8, okay? 8 times 8. 8 is 2 times 2 times 2. This 8 is 2 times 2 times 2. Okay, well, let me see. maybe I do love it now. Maybe I do love the 64. Why? Because you see, 64, that's a 4, times a 4, times a 4. Hey, listen. After all, I do love the 64 because 64 is also a perfect cube. So 64 is a perfect square, which I love if this was an index of 2. And 64 is a perfect cube. Nice. I do love it after all, okay? I'm sorry. I thought I didn't, but I do. Put a heart there. It's a perfect cube. It's 4 times 4 times 4. So what is the cube root of 64? 4. Okay? This is the way we simplify radicals. Okay? This is the way we simplify radicals. All right. How about the following? What about the square root of I'm going to say 9 times a to the, should I go there? To the third. Yeah. Okay. All right. This is a factor of 9. That's a perfect square. So you can put a heart on top of this one. That's a perfect square. Put a heart there. Is that a perfect square? No. Look at the power of 3. Okay, no problem. So I'm going to say this is the square root of 9. And I'm going to factor this. I'm going to follow that. Factor a cube. A cube is a squared times a. Okay. I love the 9. I love the a squared. This a is not my fault. I'll just leave it inside. So therefore the answer here is 3. A, the square root of a. Okay. All right. Okay. Let's do another one. How about this one? Let's do this one. What about the square root of, let me see, 9. Should I use 9? No. Oh, here's 1. No, let's not use that one. How about 3? A to the 9th. Okay. Well, I can tell you right away, I do not love the 3 because the 3 is not a perfect square. I'm looking for perfect squares now. How about a to the 9th? When it comes to variables, let me show you what perfect squares are. Okay? Watch this. Watch this. When it comes to, for variables, perfect squares. Okay, if you take a and you square it as a perfect square, so x squared, okay? If you take x squared and you square it, you get x to the 4th. X to the 4th, that's a perfect square. Okay? Okay? So, where can I go? The next one, another perfect square. If you take x cubed and you square it, you get x to the 6. Anytime you square something, you get a perfect square. So you take x cubed and you square it, you get x to the 6. That's a perfect square. This is a perfect square. Okay? What's another one? What's another perfect square? X to the 8th is a perfect square. How do I know that? Well, that's x to the 4th. Square. Anytime you square something, you're going to get a perfect square. So here I square x to the 4th and I get x to the 8th. Okay? What's next? X to the 10th. X to the 10th is a perfect square. Why? Because x to the 10th is x to the 5th quantity squared. That's x to the 10th. Okay? Okay. Wait a minute. X to the 8th is a perfect square. X to the 10th is a perfect square. But I have a to the 9th. Is a to the 9th a perfect square? No, it isn't. Okay. So what are we gonna do? Guess what? If the radicand is not a perfect square, we will factor. Okay. Let's factor this a to the 9th. Look, a to the 9th is right here in between. This is a to the 8th and a to the 10th. A to the 9th is there. So what I'm going to do is I'm going to factor a to the 9th, and I'm going to factor it trying to get what I love. And what I love is a to the 8th. A to the 9th is right there. I'm going to use a to the 8th. Okay, that makes sense. So therefore this is the square root of 3, a to the 8th times a to the 1st. A to the 8th times a to the 1st is a to the 9th, but a to the 8th is what I love. I love a to the 8th. I do. By the way, what has been squared to get a to the 8th? Or what has been squared to get x to the 8th? Well, x to the 8th is x to the 4th times 2. X to the 4th has been squared. So therefore, I ask you, what is the square root of a to the 8th? That's a to the 4th. A to the 4th comes out. The square root of this 3 stays inside because, hey, it's not your fault. And this a also stays inside. Okay? And now we have simplified this one. Look, it's been simplified. Okay? Let's do another one. All right? Do one more. How about this one? What is the square root of 49x to the 49th? Do I love 49? Do I love the factor of 49 in this radicand? Yes, I love this one. Do I love x to the 49th? No, I don't. X to the 49th is not a perfect square. It isn't. Okay? X to the 49th is not a perfect square. Watch this. X to the 48th is a perfect square. X to the 50th is a perfect square. What has been squared for x to the 48th? X to the 24th has been squared. What has been squared for x to the 50th? X to the 25th has been squared to get x to the 50th. But x to the 49th is in between. X to the 49th is not a perfect square. So it seems to me that in order for a variable to a power to be a perfect square, the power must be divisible by 2, the index. This power must be divisible by the index 2. 49 is not divisible by 2, so therefore 49 is not, x to the 49th is not a perfect square. Okay, so no problem. No problem. X to the 49th is in between. Right here. This is x to the 49th. X to the 49th right there. Okay? Not a perfect square. No problem. Let's factor. Highlight this. Factor. Factor x to the 49th. And your factors, one of them should be a perfect square. Okay, I love this one. X to the 49th, I don't love because it's not a perfect square. I got a factor. No problem. I'll take x to the 48th. That's what I'm looking for. So therefore, this equals to the square root of 49 x to the 48th. Take the smaller one, okay? 49th is in between. I'll take x to the 48th times x, and that gives you x to the 49th. But what's convenient about this? The fact that now this is a perfect square. Yes, it is. I put a heart there, and I will put a heart there because I love them. That's what you do to simplify. And what's the answer? The square root of 49 is 7. The square root of x to the 48th, what did we square to get x to the 48th? X to the 24 was squared. So what is the square root of x to the 48th? X to the 24th. Hey guys, just take 48 divided by 2. The index here is 2. Just take 48 divided by 2, you get that. And so therefore this equals the square root of, this stays inside x. Okay. Here's one more. Here's another one. What is the square root of, actually the cube root. What is the cube root of 16 x to the 20th? Let's find the cube root of 16x to the 20th. Okay, now I'm looking for perfect cubes. 16 is not a perfect cube. 16 is a perfect square. Remember before, 64 was a perfect cube and a perfect square. That was nice. But 16 is only a perfect square, not a perfect cube. Okay, no problem. What about x to the 20th? Is x to the 20th a perfect cube? The answer is no. How do you know that right away? Because this 20 is not divisible by 3. 20 is not. This power 20 is not divisible by 3. Okay? So I don't see a problem with 16, okay? So, watch this. Okay, let's, 16, what's a factor of 16 is a perfect cube? 8. So this is the cube root of 8 times 2. Oh, what about x to the 20th? Let's see, x to the 20th. So we have the following. We have x to the, watch this, x to the 17, x to the 18th, x to the 19th, x to the 20th, and x to the 21st, x to the 22nd. Okay? Which one of them are divisible? Which powers are divisible by 3? If a power is divisible by 3, then it's a perfect cube. Is 17 divisible by 3? No. So x to the 17th is not a perfect cube. Is 18 divisible by 3? Yes. So this x to the 18th is a perfect cube. Is 19 divisible by the index 3? No. So x to the 19th is not a perfect cube. X to the 20th is not a perfect cube. X to the 21st is a perfect cube. Yes, they are. So the ones that we love are x to the 18th and x to the 21st. We love them. Okay? We have x to the 20th. Okay? Well, you cannot get this one because this x to the 21st is more than x to the 20th. And here we just have x to the 20th. So we have no choice but to factor x to the 20th using this one, x to the 18th. So therefore, x to the 20th is x to the 18th times x what? Squared. X to the 18th is a perfect cube and 8 is a perfect cube. Okay, so in x to the 18th, in this x to the 18th, what has been cubed? That's a good question. What has been cubed in x to the 18th? X to the what? 6. Okay, why? Because x to the 6th to the 3rd, multiply the powers according to the power rule, and you get 18. So therefore, this becomes, what is the cube root of 8? 2. What is the cube root of x to the 18th? X to the 6. The cube root of 2x squared. And there you go. You have simplified this. Okay? You're going to keep using this rule. Okay? Okay, one more thing I have to say. I have to say the following. Okay? I have to say the following before we're done with this. I have to say the following. And this is what I need to say. I need to say that whenever, and where is it? Oh, it's on page 589. Look at page 589, where it says simplifying the nth root of the nth root of x to the nth. It says this. It says the following. The nth root of x to the nth. It says, if x is a real number, okay? If x is a real number, then, look at this. If n is odd, is an odd natural number, then the nth root of x to the nth equals just x. If n is an even natural number, then the nth root of x to the nth is the absolute value of x. Okay. Let me try to make sense of this for you guys, okay? Look, basically this is what they're saying. If we're considering x to be any number that comes to your head, any number on the number line, positive, negative, okay? What they're saying is this. The square root of x squared, they're saying, is the absolute value of x. That's what they're saying. Okay? If x is any real number. Okay. Oh, and they also say if x is any real number and n is greater than 1, that's fine. Okay? So, that means that whenever you have, if we don't define if we say x is any real number, for example, we have the following example. Find the answer to the following. Find the answer to the square root of, let's say 8x to the 13th. Okay? Let's find that answer. Well, let's use this. Let's find factors of 8 that are perfect squares, factors. Okay, no problem, I got that one. This is the square root of 8 is 4 times 2, or 2 times 4. What about x to the 13th? That's x to the 12th times x. Okay? We love the 4 and we love x to the 12th. Because of this rule. Right here. Okay? Because of this rule, we're going to say the following. We're going to say, in this case, we get a 4. Okay? And we get Actually, in this case, it doesn't make sense. It does not apply because x to the 6 is always positive anyways. Okay, the square root of 2x. All right. Here, I think I have to give you a better example. Here's a better example. What is, another example. What is the square root of, what is the fourth root of, I'm gonna say 20. X to the 5th. Okay, this is gonna apply here. Well, this equal, now we're looking for perfect. A number to the 4th power. So therefore this equals to the 4th root of 20. X to the 4th, x. You see, for any real number x, we have to apply this rule. If n is an even natural number, in this case, n is the index. Look, n is the index. The index and this power are the same. Index and this power are the same. We have to say that this equals to, look at this, the nth root of x to the nth equals the absolute value of x. So therefore, this 20 you can't do anything about. It stays inside. So therefore, we're gonna get the absolute value of x for the 4th root of x to the 4th. That's the absolute value of x. And then times the 4th root of what? Of 20 times x. That's what they're saying, okay? All right. We're done, guys. We're done, okay? Let me see if what I wanted. Oh, I have a few more things to say and then we're done. Okay? We're done, almost. Okay, let me get another marker because this one is running low, okay? All right, here we go. So look at the following. Consider this. Sometimes we're going to have to add and subtract radicals. Whenever we add or whenever we subtract radicals, we must simplify each radical. What am I talking about? I'm talking about this one. Consider the following problem. Take, for example, this. Okay, let me say this first. Like radicals have the same index and the same radicand. Also, we always combine, that means add or subtract, add, subtract, like radicals. Yes. It's like adding like terms. We do the same thing with radicals. Whenever they are like radicals, we combine them, we put them together. We add them or we subtract them. Whatever we have to do to combine them. Well, consider the following. Consider this. 14 plus 3, the square root of 75, minus 2, the square root of 12, plus 2, the square root of 48, minus 8. Here we go. Look at this. So, like radicals have the same index and the same radicand. So, the index is 2, the index is 2, and the index is 2. This one has no radical at all. But my question is this one, and that one, are they like radicals? Well, they must have the same index and the same radicand. Okay, they all have the same index right here, this one, and that one, but do they have the same radicand? The answer here is 75, 12. No, they don't. And so the question is, are they like radicals? The answer is this. Don't judge yet. We don't know until you simplify them. Then you can judge. Okay, you can't just judge, I don't know, a book by its cover. You have to simplify. You have to open the book and look at it. So here you have to simplify this radical. You have to simplify this radical, and you have to simplify this radical. Simplify means go through this. And then you can judge the book by its cover. So here we go. I'm going to keep the same problem as it is, okay? I know I can take 14 minus 8 is 6, but I'm going to keep it the way it is right now. So this is 14 plus, and I'm going to simplify this. So this is going to be 3, and to simplify this, I'm looking for perfect squares. There are factors. Factors of perfect square. What's a factor of 75 that's a perfect square? 25 times 3 minus 2 times. I'm looking for factors of perfect square. What's a factor of 12 that's a perfect square? 4 times 3 plus 2 times 48. The square root of, what's a factor of 48 that's a perfect square? 16 times 3 minus 8. Oh, look, guys. 75, 12, and 48. You would say, well, wait a minute, they are not like radicals. Don't judge until you simplify. Look what happened. Now, I'm going to simplify this together. That's a perfect square. Love it. I love it, and I love it. So this is 14 plus a 5 comes out, and it gets multiplied times 3. 5 comes out. What's the square root of 5? Is 5 times 3, 15. The square root of 3. Minus. A 2 comes out, and that 2 is multiplied times negative 2. What's 2 times negative 2? Negative 4. The square root of 3. Plus. A 4 comes out. What's 4 times 2? 8. The square root of 3 minus 8. Look at that. Guys, you saw here, there, and then you said, no, they're not like radicals. No, you don't know that. You need to simplify. This became this one, and that one. Look, they are like radicals. Yes, they are. 3, the square root of 75, can be combined with negative 2, the square root of 12, plus 2, the square root of 48. They can be combined. Yes, they can, because they are like radicals. They all have 3, 3, and 3 as a radicand. So all we're going to do now is combine. I'm going to take the 14, subtract 8, and that's a 6. I'm going to take the 15, the square root of 3 minus 4. Square root, what's 15? Square root of 3 minus 4, square root of 3, that's 11, the square root of 3. 11, the square root of 3, plus 8, the square root of 3, isn't that 19? So that's going to be plus 19, the square root of 3. And that's what I mean. So here, you can't judge. You need to simplify and then judge. How do you simplify? Use that. Okay? Here's the last problem, okay? Here is the last problem. Gotta erase this, guys. I'm sorry, okay? Erase it. Here's one more. Try this one. Good people, try this one. Try the cube root of 24 minus the cube root of 16 plus the cube root of 54. And we ask the question, are these like radicals? And what's the answer? You can't judge yet. Don't judge. Do not judge before simplifying the radicals. Once you simplify the radicals, then you can judge. Okay. So let's simplify first. What is a factor of 24? That's a perfect cube. So this is the cube root of 8 times 3. That's 24. Minus, what's the square root of 16? That's a perfect cube. That's the cube root of 8 times 2. That's 16. Plus, what is the cube root of 24? Factor of 54, that's a perfect cube. 27. So this is the cube root of 27 times 2. Now simplify. The cube root of 8 is 2. The cube root of 3 minus the cube root of 8 is 2. The cube root of 2 plus the cube root of 27, which is 3, the cube root of 2. Okay, now the question back. Back to the question. Okay, are these like radicals? The answer is not all of them. This one and that one, they are like radicals. Not this one. That one has a radicand of 3, and these two have a radicand of 2. So those two are like radicals, not this one. So this one, it stays by itself, and we combine those two. So therefore, this is 2, the cube root of 3. Let's combine those two. Just add, I call this the coefficient. What's minus 2 plus 3? That's 1. So plus 1, the cube root of 2. There we go. Okay, good guys. All right, good class. Okay, today I did section 7.1 and 7.3. Okay, we'll come back with section 7.2 next time. All right. Have a very nice day. I'll see you guys soon. Okay. Bye.